Let's again imagine that we have placed our polarizer with its optical axis parallel to the ground. Thus, we have adjusted the measurement procedure, which is defined by the 0, 1 basis. And imagine that the photon we are going to measure is in the state plus, which is the state right between our basis states. For the measurement of this photon in this basis, we have two equiprobable outcomes. First, the photon passes through the polarizer and obtains the horizontal polarization, thus jumps to the state 0, or the second, it reflects from the polarizer, jumping to the state 1. We already know enough to understand this situation. These completely random outcomes tell us that the photon actually takes both these opportunities. It passes and reflects simultaneously, though in different universes. And we subjectively perceive only one of these outcomes. And if the photon does both things, then we can assume that before the measurement, this photon actually was in two states simultaneously. It was in the state 0 with horizontal polarization and in the state 1 with vertical polarization. Now, each of these photons, from the point of view of the wave theory of light, is represented as a wave. But what is a wave? Waves propagate oscillations. So to understand what is a wave, let's start from the question, what is oscillation? For the sake of clarity, we are going to consider the case of a simple harmonic oscillations, which are described by the differential equation written here. In this equation, f stands for the parameter which oscillates. It can be, for example, the position of a pendulum, or its velocity, or it can be the intensity of electromagnetic field, etc. The letter omega denotes the angular frequency of oscillations. We will see what it means later. And the letter t denotes time. So the function f is a function of time. Okay, let's take a closer look at the equation. First, we can note that this equation is a linear differential equation, which means that if two functions f and g satisfy this equation, then any weighted sum of these functions also satisfy this equation. Second thing to notice here is that we differentiate the function f two times, and we obtain just the same function, but with the minus sign. From mathematical analysis, if we consider only real-valued functions of real variable, we can remember two functions which satisfy this condition. These are sine and cosine. If we differentiate sine two times, we obtain minus sine, and same with cosine. Sine and cosine are actually the same thing. They just differ by the phase. So we can write the basic function which solves this equation as this. Here, a big stands for the amplitude of the oscillations, omega is an angular frequency, and the new letter phi defines the phase of oscillations. Let's see how this works. At time 0, the value of f is just a big multiplied by cosine of angle phi. The cosine has a period equal to 2 pi. So after the time interval 2 pi divided by omega, we will have the same state of the oscillator, a big multiplied by cosine of phi. This means that the period of oscillations equals to 2 pi divided by omega. And since in the same time it is 1 divided by the oscillation's frequency, nu, we can conclude that Angular frequency is just wave frequency nu multiplied by 2 pi. Okay, now what about this phi, which denotes the phase? If phi equals to 0, then at time 0 we have function f equal to its amplitude, which is its biggest value. If phi equal to pi divided by 2, then function f at time 0 is 0, which is the central position of oscillation. With phi equal pi, we have the same oscillations, but with the reverse sign. When initial oscillations with the 0 phase have value x, the oscillations with the phase pi have value minus x. And with the phase phi equal to pi, we will have exactly the same oscillations as with 0 phase, since 2 pi is the period of the cosine. So phi has the physical meaning of the phase shift, which tells us at which point of the cycle the oscillations are at time 0. Okay, sines and cosines work pretty well if you consider the real-valued functions. But what if we look at the functions which values can be complex numbers? I mean, let's take a look at this equation again. We differentiate the function and we obtain the same function, multiplied by a constant. For a mathematician, it really does ring a bell. The only function with this property is exponent. When you differentiate the exponent, you obtain the same exponent multiplied by the derivative of its parameter. And since we differentiate it twice, we must obtain the same exponent again, but multiplied by the derivative of its parameter 2 times. So for the exponent of omega t, after double differentiation, we obtain omega squared multiplied by exponent of omega t. Not good enough, since we want to have this minus here. How can we obtain a negative number after squaring something? With complex numbers, it's easy. We need just add here an imaginary unit. And the whole solution in complex numbers looks like this. A big is again the amplitude, and phi is a phase. It looks all good, but there's one question. This function is a complex valued function. How can we interpret it or use it in our real world for describing real oscillations? There are no complex numbers in the real world, right? Well, it's okay. When we want to obtain the physical meaning of this function, we just have to omit the complex part. This exponent can be rewritten using Euler's formula like this. Now, when we consider the physical meaning of it, we keep this real-valued cosine and forget about the imaginary part, I multiplied by sine. And we obtain just the same expression as before. But what for? Why do we need to do all this with complex numbers if we can do it with the real numbers? And the result is just the same. Well, there's a reason. Remember what I told you about vector spaces and particularly about the state space. I told you that multiplication of a state by a number does not change state. Now let's consider the oscillations with zero phase shift. I wrote here the functions which describes them. The real valued function is on the left and the complex valued function is on the right. Now, what if we add some phase angle phi? For the real valued function, phi goes into the argument of cosine. But for the complex valued function, adding phase is just multiplication by a constant. And this multiplication does not even change the length of the vector. So, if we consider the state space over the complex numbers rather than the real numbers, then phase shift is just a multiplication by a constant, and thus it does not change the state. This property of complex valued functions is just so convenient that physicists almost never describe oscillations and waves in the terms of real valued functions. You can always see these complex exponents everywhere when waves are considered.